All right, everyone, let's get into it. The midterm is right around the corner, and I know that can be a little stressful, so we're going to walk through all the core concepts together, step by step. The whole point of this is to make sure everything really clicks into place, to connect the big ideas so you can walk into that exam feeling totally prepared. We're not going to rush, we're going to take our time and make sure it all makes sense.
And just so you know, everything we're about to cover comes straight out of the textbook you've been wrestling with all semester. Good old Griffiths. So there are no surprises here, no new material, no curveballs. We're just taking a really focused, deep dive into the key ideas, the essential equations, and the problem-solving methods that are the absolute bedrock of this course.
So, here's our game plan for today. We're going to start with the two absolute main characters of the story, the wave function, psi, and the Hamiltonian, h. Then, we'll get into what I think is the master key for solving problems, stationary states. After that, we'll put it all to work on a classic exam problem, the harmonic oscillator. From there, we'll zoom out and look at the abstract rules of the game, apply them to a spin system, and then wrap everything up with a final recap and some last-minute tips.
Okay, let's dive right in. Every theory has its core elements, right? And for quantum mechanics, you can't get anywhere without understanding the two stars of the show, the wave function, which we write as a capital psi, and the Hamiltonian operator, h. Seriously, understanding their roles and how they interact, that's the first step to understanding literally everything else we're going to talk about. So first up, what in the world is this wave function, this psi of x and t? Well, it's the central object in our whole story, but it's a bit abstract. So let's be super clear on this. It is not the particle. You can't reach out and touch the wave function. Think of it more like a complete information packet. Everything you could possibly want to know about a quantum system, its position, its momentum, its energy, you name it, it's all encoded right there inside its wave function. Now, its real power comes from what we call its statistical interpretation. If you take the square of its magnitude, that's the modulus squared of psi, what you get is the probability density. It tells you the probability of finding the particle at a certain spot at a certain time. And that's the key right there. Quantum mechanics is, at its heart, all about probabilities, and the wave function is the mathematical tool that gives us those probabilities. And this beast is the equation that tells the wave function what to do. This is the time-dependent Schrödinger equation. It's the master equation of all quantum dynamics. Now, I know it looks intimidating with all the symbols, but its job is actually pretty familiar. It's the quantum version of Newton's F equals ma. If you know the state of your system right now, this equation tells you what its state will be at any time in the future. So let's break it down. On the left side, you've got how the wave function changes in time. Simple enough. On the right side, all that stuff is the Hamiltonian operator, h hat, acting on the wave function. This first term with the second derivative, that's the kinetic energy. And this v term, that's the potential energy. And what do you get when you add kinetic and potential energy? You get the total energy. So the Hamiltonian is just the total energy operator. That's all this equation is saying. The way a quantum state evolves through time is dictated by its total energy. Okay, so trying to solve that full time-dependent equation directly for every single problem is really, really hard. Most of the time, it's just not practical. But lucky for us, there's an incredibly powerful trick, a beautiful method that makes our lives so much easier. So let's talk about what I like to call your absolute best friend for this course, the idea of stationary states. These are special, simple solutions that make everything else manageable.
So how do we find these magical stationary states? We use a classic mathematical technique called separation of variables. The logic is so important, so let's walk through it nice and slow. First, we just make a guess. We assume that our full wave function, capital psi, can be split up and written as a product of two separate functions. One part, we'll call it little psi, depends only on position, x. The other part, we'll call it phi, depends only on time, t. Okay, so we take this guess and we plug it back into the big, messy Schrödinger equation. Then we do a little bit of algebra. Basically just divide by psi itself and we rearrange things. And what we can do is get every single term that has a t in it onto the left side and every single term that has an x in it onto the right side. Now, stop and think about that for a second. We have a function of only time equal to a function of only position. How is that even possible? I mean, if I change t, the left side has to change, but the right side can't care because it has no t in it. The only way this can be true for all x and all t is if both sides are actually equal to the exact same constant. And here's the beautiful part. In quantum mechanics, that constant has a physical meaning. It's the total energy of the state, which we call E.
So this whole separation process does something amazing. It takes that one really hard equation and splits it into two much simpler ones. The time part is easy to solve, and the space part gives us this,
the time-independent Schrödinger equation, or the TISE. And this is a huge point, so don't miss it. The TISE is not a new law of physics. It's a tool. It's a special equation we use specifically to find these stationary states. And just look at its form. H hat on psi equals E times psi. That's an eigenvalue equation. The Hamiltonian operator acts on the wave function and just gives you back the same wave function, multiplied by a number, the energy E. The solutions, the little psi functions, are stationary states. And why do we care so much? Because these states form a complete set of building blocks. Once we find all the stationary states for a system, we can build any possible solution by just adding them up in a superposition. You solve the TISE one time, and you've got the fundamental pieces to describe the system for all time.
Okay, so we have our main strategy. Separate variables, solve the TISE to find the building blocks. Now let's put that strategy to work on one of the most important systems in all of physics, and I promise you, an absolute star of pretty much every quantum exam, the harmonic oscillator. It pops up everywhere, and we're going to tackle it using a really slick algebraic method that uses something called ladder operators. Now, you could solve the harmonic oscillator problem by grinding through a really nasty differential equation, but why would you want to? Instead, this algebraic method introduces two brand new operators. They're built out of the position and momentum operators we already know, but in a really clever combination. We get A plus, the raising operator, and A minus, the lowering operator. Now, for the moment, don't even worry about what they look like mathematically. The important thing is what they do, and their names give it away. They are literally tools that let you walk up and down the ladder of allowed energy states, one rung at a time. It's an incredibly powerful way to find all the solutions without solving any painful differential equation.
The entire magic of this ladder operator method comes from one single fundamental relationship. It's the relationship between the position operator, x hat, and the momentum operator, p hat. It's this formula right here, which Griffiths calls the lovely and ubiquitous canonical commutation relation. The commutator of x and p, which is just a shorthand for x hat times p hat minus p hat times x hat, it isn't zero. It's equal to this constant, I times h bar. Now, this is not just some mathematical curiosity. This one little equation is basically the weird beating heart of quantum mechanics. It means that position and momentum don't commute. The order you apply them in matters, and physically that means they are what we call incompatible observables. You cannot, even in principle, know the exact position and the exact momentum of a particle at the same time. This simple formula is the mathematical seed from which the entire Heisenberg uncertainty principle grows.
So how do we actually use these things? Well, the process turns into a simple, repeatable recipe. Step 1, you find the ground state, psi 0. That's the state on the bottom rung of the ladder. It has the lowest possible energy. And how do you know it's the bottom? Because you can't go any lower. So we find it by solving the simple equation. The lowering operator acting on psi 0 gives you 0. Once you have that ground state, the rest is honestly pretty easy. To get the next state up, the first excited state, you just hit the ground state with the raising operator. Want the second excited state? No problem. Just hit the first excited state with the raising operator again. It's like an engine. Every single time you apply the raising operator, you climb one rung up the ladder and you add exactly one quantum of energy, h bar omega. It's a beautiful algebraic machine that just churns out all the solutions for you.
All right, let's just take a step back for a second. We've talked about the Big Master equation, and we've used this really cool ladder trick for a specific problem. Now, let's zoom out and see how these specific ideas are actually part of a much bigger, more general, abstract framework that governs all of quantum mechanics. It's time to talk about the formalism.
Okay, so you're going to hear this term Hilbert space thrown around. And I know it sounds really intimidating, but the basic idea is actually not that bad. Just think of it as the arena, the stage where quantum mechanics happens. You know how a normal vector, like one with x, y, and z components, lives in regular three-dimensional space? Well, a quantum state, our wave function, lives as a vector in this abstract mathematical space we call Hilbert space. It's just the name for the mathematical playground that has all the right rules for quantum mechanics to work.
So if the states are vectors in this space, what about the things we actually go out and measure? Like position or momentum or energy. In the formalism, we call these things observables, and each one is represented by a special kind of operator called the Hermitian operator. And they have one property that is absolutely 100% crucial. They are guaranteed to always have real eigenvalues. And why is that so important? Well, when you go in a lab and measure something, you get a real number, right? You measure 5 meters or 10 joules. You never measure a result like 3 plus 2i joules. That would be meaningless. Hermitian operators are the mathematical guarantee that our theory will always predict real number answers for real-world measurements.
And this is the moment where it all clicks together.
I really want you to lock this in. This whole abstract formalism, it isn't some weird new thing. It's a generalization of what you have already been doing this whole time. Just look at the time-independent Schrödinger equation again. H hat on psi equals E times psi. That is exactly the form of an eigenvalue equation. The Hamiltonian, H hat, that's the Hermitian operator for the observable we call energy. The stationary states, the little psi's, those are its eigenfunctions. And the allowed quantized energies, the E's, those are its real eigenvalues. See? We've been doing it all along. The formalism just says, hey, this powerful idea works for everything, not just energy.
So the big takeaway is that this whole operator eigenvalue structure is universal. It's the core logic of quantum mechanics. And to really prove that to ourselves, let's apply this thinking to a problem that doesn't involve wave functions or derivatives at all. Let's look at a totally different kind of system, quantum spin, and specifically, the Heisenberg-Hamiltonian.
So here's the type of problem you might see. The Heisenberg-Hamiltonian describes the energy that comes from the interaction between two little quantum magnets, two spin 1/2 particles, like a pair of electrons. The Hamiltonian is just H equals J times the dot product of their two spin operators, S1 and S2. That J is just a number, a constant, that tells us how strong the interaction is. And our job, well, it's the same job as always in quantum mechanics. Find the allowed energies of this system.
So how do we solve a problem like this? We follow the exact same quantum strategy, it's just that the mathematical objects look a little different. The parallel is perfect. Before, when we were dealing with position, our states were functions, psi of x. Now, for a spin system, our state vectors are just little columns of numbers, which we call spinners. Before, our operators were things with derivatives, like the momentum operator. Now for spin, our operators are matrices, like the Pauli spin matrices. But here's the key. The fundamental goal is identical. We need to find the eigenvalues and the eigenvectors of the Hamiltonian matrix. The eigenvalues will be the allowed energies, and the eigenvectors will be the stationary states. The math changes from calculus to linear algebra, but the core quantum physics, the strategy, is exactly the same.
All right, deep breath. We have covered a lot of ground, all the way from the foundational Schrödinger equation to the abstract rules of the game and even a spin system. So now let's boil it all down. Let's condense everything into the most critical, high-yield points that you absolutely need to have sharp in your mind for the midterm. Think of this as your final checklist.
Okay, let's run through it, one by one. First, the time-dependent Schrödinger equation is the master law. It tells you how any state evolves in time, period. Second, your number one problem-solving trick is separation of variables, which gets you to the time-independent Schrödinger equation, H psi equals E psi, whose solutions are your stationary states, your building blocks. Third, every single thing you can measure is represented by a Hermitian operator. Fourth, the only possible results you can ever get from a measurement are the eigenvalues of that operator. No other values are possible. And fifth, that little commutation relation between position and momentum, that's the deep mathematical reason for the uncertainty principle. If you can internalize these 5 points, you will have a rock-solid framework to tackle any problem they throw at you.
And look, if you start to feel overwhelmed or lost during the exam, just take a breath and come back to this one central strategy. I promise you, it works for every single problem. The infinite square well, the harmonic oscillator, those spin systems we just talked about, they all boil down to this. Step 1, figure out what the Hamiltonian is for the system in the problem. Step 2, find its eigenvalues and its eigenfunctions. That's the whole game. Everything we have done today is just a variation on that single fundamental theme.
Okay, so take a second and think back over that checklist. Is there one of those points that still feels a little fuzzy? Maybe it's the logic of separation of variables, or you're still not totally sure what a Hermitian operator really is. Whatever it is, that's your signal. That's where you should focus your last bit of studying. Go back to that chapter in Griffiths, work through one more example. You've put in the hours, you've seen how all these different pieces connect to each other. You are ready for this. Seriously, you've got this. Good luck.